strings, everything that he has to all that shit. I wrote it in those strings. And that was the most responsive bike I've ever written. I'm talking about you twist the throttle that much. Super responsive. And clutch was butter and like an original clutch. See, all he did was add the oil. We gave us the name. That bike was
Thank you. Let's get started.
Yeah, give it gas.
Finish your conversations about whatever you're talking about, parking or whatever. Okay, ready? Start? Thank you. Okay, fog. Fog is a cloud on the surface. Pretty easy, right? So fogs are clouds on the surface where the water vapor in the air condenses and becomes visible in the form of fog. Same as a cloud, it's just on the surface. So we categorize fog based on how it forms and how the temperature and amount of water vapor in the air causes the formation. So we're going to go through the types of fog today that you need to know. There are 4 main ones that you need to know that you'll be asked about: how they form, what are the conditions for formation, etc. So what we need to take from here is fog is a cloud on the surface. And we know that a cloud is formed when the air is cooled to its dew point. So the dew point and the temperature meet, are at the same, are the same number. They meet, they're cooled to the air's dew point. Water vapor condenses and becomes visible, in this case, in the form of fog. Okay, let's keep going. Radiation fog is the first type of fog. So this is going to be on calm, clear nights with little to no wind present. So this is important. Where's my pen? With radiation fog, little to no wind present and clear nights. Okay, these are the conditions for radiation fog. So what's happening in this picture is the ground is cooling rapidly due to terrestrial radiation. So the ground's cooling fast and reaching its dew point closer to the ground. And then when the surrounding air temperature reaches its dew point, it's creating fog from that radiation off the ground. So the fog stays right over the ground. I'm sure if you've been to like a golf course or something in the middle, not the middle, in the very like early morning, it's like a low-lying area like valleys. You sometimes get that fog that's right over the ground. It stays there usually until something heats it up enough to dissipate and move on. So like when the sun comes up, that's when radiation fog would dissipate. If there's more wind than like a couple knots, if there's more wind, that wind will push away, dissipate the fog. So radiation fog is, what's the word? Is dependent on having little to no wind present on a clear night. Clear meaning there's no other clouds above it to trap heat. So if there were more clouds above in the sky, they would trap the heat that's rising and push it back down towards the ground, and that would heat up all of this air, which would then dissipate the fog. Okay, so heat radiating from the surface at night cools down to reach its dew point. Reaching its dew point is the formation of fog. Okay, so then a layer forms right on top of the ground. Radiation fog. Good. Cool. We'll keep moving. Advection fog. You're going to be asked about this a bunch of times because it's the most relevant fog to the area that we're training in. So Warm, moist air moves over a cold surface from the water over to land. So that's important to our area because we're right by the coast, right? So that water from the ocean creates a warm, moist air mass that moves over a cold surface, as in the ground of land. So warm, moist air. Here we go. Warm, moist air moves over a cold surface. When it moves over the cold surface, it cools to its dew point and fog forms. So, unlike radiation fog, also important, wind is required for advection fog because that wind has to push the air mass from the water over onto land. So 15 knots is what we're looking for. So this is like 15 knots is like a common sea breeze that you get from the ocean. Very common to have 15 knots coming from the water. So around up to 15 knots allows fog, advection fog to form. If you get much higher than that, then it's talking about it usually just lifts into the air and forms low stratus clouds instead of fog on the ground. Okay? Coastal areas. So when they ask you in the phase check or the check ride, what is the most common type of fog you'll see in the area that we're training in here at Torrance, the answer is advection fog. Okay, because we're right by the coast, coastal areas. Sea breezes blow the air from over the water onto a colder surface of land. Thus, the air mass cools to reach its dew point, and then fog forms. Okay. Biggest thing, warm, moist air over a cold surface. Wind is required, but not too much wind, not over 15 knots, because then it forms low stratus clouds. Okay. Okay, upslope fog. It came back. Where did you all end up parking? Best Buy, okay. Sounds good. Okay. Back to upslope fog. So this is when moist, stable air is forced upwards like the side of a mountain. Okay, so there's gonna be hills and mountain terrain is gonna cause upslope fog. So warm, moist, stable air is forced upwards up the side of a hill or a mountain, and that upward force up the side of the mountain is creating upslope fog. So where's my pen? Moist, stable air, and that moist is important, right? For fog, we need water vapor in the air. We need, and then we have wind is required because that wind is what's gonna force the stable, moist air up the slope of the mountain. And they want to add here that unlike radiation fog that burns off with like the morning sun, upslope and advection fog can persist for days. It's not enough heat from the sun rising to dissipate upslope and advection fog. But like I talked about, radiation fog usually dissipates with like the sun rising. Yeah. They extend greater heights than radiation fog, obviously because radiation fog is right here on top of the ground, and this has wind that's pushing it up the side of a mountain or a hill. Okay, as the air rises, again, it cools to its condensation temperature. It cools to the dew point and creates condensation, which creates a cloud. Okay, no question. Steam fog is a little more rare. It's not one of the main four that you're gonna have to talk about, but steam fog or sea smoke is what it can be called because it's over warm water. So it's the opposite of advection fog. So cold, dry air moves over warm water, as opposed to advection fog is warm, moist air moving over cold land, cold surfaces. Steam fog is when cold, dry air moves over warm water, okay? Cold, dry air over warm water. So the air is going from the surface, cold air, and moving over moist, warm air, obviously because it's over the water. So the water evaporates over, as water evaporates over the warm surface of the water, it rises and resembles smoke. So that's why they call it sea smoke. Yeah, common over water, obviously you need the warm water during the coldest times of the year. So when the surface of land is colder than water, this is going to happen because the water is going to be warmer than the surface of the ground. And then they also want you to know low level turbulence and icing are commonly associated with steam fog. So we have the warm water, cold air moving over warm, moist water. It evaporates and rises off the water looking like steam. Okay. Okay, ice fog. Okay, this is mainly in Arctic regions, also rare that we're going to see this anywhere around us because the formation has to be such a cold temperature that we're never going to reach anywhere around here. So they have it as -25 degrees Fahrenheit or colder here. So obviously ice fog is occurring when cold weather, when the temperature is below freezing, much below freezing. Do we know what temperature freezing is that? Good, and then Celsius, 0 is easy for Celsius. Okay. So water vapor is forming directly into ice crystals because it's so cold. So as it's condensing, as it's reaching its dew point, instead of forming clouds, it's forming directly into ice crystals. Okay. Okay, yeah, so it's comparing it to radiation fog, except for how cold the ground is. So it's working sort of like radiation fog in the formation, except when that air on the ground is reaching its dew point, it's forming directly into ice crystals and creating ice fog. Okay. Yeah, Arctic regions. All right, that should be all of the fog. Do we need to go back to the first types of fog for you guys, or you have it written down? We can go back real quick.
That's fog is steam fog.
We have two before that. They're a little more important, actually. So radiation fog. Since we talked about it, who can explain radiation fog? Yeah, go ahead.
So they're nights and there's no wind presence. It's when it's warm air going over a cool surface.
That's back to advection
Advection.
fog. So this is like the ground, the
Warm
heat from the
surface.
ground.
Okay, so the heat from the ground rising,
Mhm.
creating.
Yeah, the radiation from the ground that they're talking about, the heat radiating from the surface of the ground at night. When that air rises, it cools down to its dew point, meeting its dew point, which means the air is now saturated and forms fog. Okay. The ground cools rapidly due to what's called terrestrial radiation, radiation from the ground. We talked about how there's little to no wind presence. With this is important. It's on clear nights where there's not other clouds up higher in the sky. And we can see this like over a golf course or in a valley in early morning. You'll see fog on top of the ground. Yeah, and it usually dissipates when the sun comes up. So this is only found like early mornings on clear nights. After usually in the winter, after a long winter night that it has time to form. And then as soon as the sun comes up and starts heating up the air again, the fog dissipates over the ground. So this is really just early mornings before the sun has come up. Clear nights, no wind. The heat radiating from the ground rises and cools to the dew point, reaches the surrounding air temperature, reaches its dew point. It condenses and forms. We talked about in the first slide too, fog is just clouds that are on top of the ground over the surface, right? So they form the same, fog forms the same way as clouds do in the sky. This is just clouds over the surface of the ground. Cloud that is on the surface, okay? And then quickly go back to advection fog. Who can tell me how advection fog is formed? You could even read it off of the TV, someone. Yeah, Alex, go ahead.
Air for.
Yes. Warm, moist air from the water moves over a cold surface. You need wind to be present for this to form because you need that wind to blow the warm, moist air from the water over the colder surface. And this is common in coastal areas. So this will always be the answer when they ask you what's the most common type of fog or torrents or for the area that you're training in. It's always going to be advection. Okay. Then we just went over these. So now we're done with fog. We'll get to clouds. Okay. There's different types or classified clouds. So we have low, middle, and high clouds, and then clouds with vertical development are its own type. So this is by height, shape, and other characteristics. So we're going to talk about each of these, have a slide for low, middle, and high clouds. But we obviously know for clouds to form, there has to be adequate water vapor in the air. You need visible moisture and condensation. That's the method by which the air can be cooled. So the air has to be cooled to reach its dew point, and then the water condenses, the water vapor condenses and forms clouds. And we're talking about clouds because they're visible indicators of future weather. So we already talked a little bit about this, and we'll get into it when we get into each of the types of clouds, but we talk about how certain type of clouds are associated with stable and unstable weather, right? So those are visible indicators. We're going to keep going because it's going to get into each one of these individually. All right, low clouds. They have the altitude here for you on near the Earth's surface up to 6,500 feet AGL. Primarily made of water droplets, but it can also include supercooled water droplets. We're going to get into icing, I think, at the end of the slides today, but supercooled water droplets are what creates aircraft icy. Because as we fly the airplane through supercooled water droplets, they're freezing on the surface of the plane almost immediately because they're already cooled to the point of freezing. If we were flying through actual frozen water droplets, they would be able to hit the plane and kind of break up. But because they are water droplets, they're still in the form of water, they would get on the plane, and because they're already super cooled almost to the point of freezing, they would freeze on the surface of the plane and build up, especially on the wings. But we'll talk about that later. Types of typical low clouds: stratus, which we've already talked about, stratocumulus, and nimbostratus. Do we remember what nimbo means? Yeah, water. This means water, rain is associated with this cloud, okay? Stratus is the big one. Then your stratocumulus is just like a mix of cumulus and stratus clouds. But stratus is the big one. We've already talked about that, right? It's the kind of thin, flat cloud. What are stratus clouds indicating for the stability of our atmosphere? Stable, good. Okay. Let's keep moving. Low clouds up to 6,500 feet AGL, stratus clouds. Middle clouds, obviously are gonna start where we ended, so 6,500 AGL, extend up to 20,000 feet AGL. These ones can also be composed of ice crystals and again, super cooled water droplets and regular water. But you're adding ice crystals up here because what's happening to the temperature as we are ascending in altitude? It's decreasing. So now we have ice crystals in play because we are at lower temperatures the higher we go. Okay, alto stratus and alto cumulus. Alto is telling us middle. This is just the, what do they call it when they put something on the front of a word? The prefix, there we go. Thank you. The prefix to a stratus or a cumulus cloud. So these are just other types of stratus and cumulus further defined into where they are in the middle, defined as middle clouds. So these are middle level stratus and middle level cumulus clouds. Okay. Whoa, someone at McDonald's? Chick-fil-A, okay. You're good. You're just stuck in this tiny box. I'm like, immediately I smelled that. No, you're good. You can eat. I don't care. I was just like, whoa. Okay, high clouds. Ooh. High clouds. Obviously, now we're going above 20,000 feet. So from 6.5 and below is low clouds, 6.5 up to 20,000 feet is middle, and then above 20,000 feet AGL is high clouds. They usually only, where's my pen? Only form in stable air. Only form in stable air. And made up of ice crystals, like we talked about. We're higher in altitude. That means we're lower in temperature. So we're able to get to that freezing point higher up. And no real threat of turbulence or aircraft icing because they're so solid in the ice crystals, like I just talked about. Flying through ice crystals up in the air is just going to break through the plane, like they're just going to bust up as we fly through them. Flying through super cooled water droplets is where those water droplets get on the surface of the airplane and freeze on the surface instead of just flying off the surface, right? So ice attached to the surface of our plane, especially our control surfaces, is where we get aircraft icing and where it's dangerous. And then up here are cirrus clouds, cirrostratus, and cirrocumulus. So again, we're adding that prefix to stratus and cumulus type clouds. And then cirrus clouds are like the really wispy ones that you see really high in the air. They're high clouds. They're really wispy. They look like this. I'm sure you've seen them. Yeah. Just how they look. So this is going to be high cirro, again with the prefix is high stratus clouds. So it's going to be the same cirro, high cumulus. So you have those big fluffy cumulus clouds. Yeah, cirrus. Yeah, how they break up and like form different shapes is how they're, so like cumulus, we're talking about like the big vertical development, like fluffy clouds. Stratus, we're talking about more like flat layers. Cirrus is like broken up into like wispy kind of cloud formations, but they're all formed the same way with reaching its dew point, condensing, forming clouds. And I think it will get into, there's also a couple extra ones, as long as we got that. I think it gets into, there's a type of cloud called a fracto cloud, which is basically like a cumulus or a stratus cloud that through wind shear or strong winds has been like fractured into different parts, so it looks like jagged on the edges because the wind has come in and like basically cut apart one of the bigger clouds. Okay, but I think those are on the next slide, so we'll keep going. Clouds with extensive vertical development. So these are going to be towering cumulus. Well, good line. Towering cumulus or cumulonimbus. Nimbus again means water, rain cloud. Okay, these clouds have or are formed low to middle region, but can extend into high altitudes. So areas, they indicate areas of instability because we talked about vertical development indicates an unstable atmosphere because what is the standard for how we determine the stability of an atmosphere? Its ability to resist vertical motion. So if there is extensive vertical development, it's not resisting vertical motion at all. It's unstable. So towering cumulus clouds indicate areas of instability in the atmosphere. Inside them is turbulent, very turbulent. Again, with being able to identify clouds visually and know what weather is associated with them will help you because if you see a cloud with extensive vertical development, a towering cumulus cloud, do you want to fly through that cloud? Probably not. It's extremely turbulent around and inside the cloud. So flying through it, you can expect a lot of turbulence. And they often develop into thunderstorms. Cumulonimbus clouds or thunderstorms. And we'll talk about, there's slides later on that talk about how thunderstorms form. There's 3 ingredients to a thunderstorm. One of them, the first one is vertical motion, vertical development. So if you have vertical development from clouds, you already have the first part of a thunderstorm. Okay? Yeah, containing large amounts of moisture because of that nimbus on the end is telling us water, rain. So obviously there's going to be a lot of moisture and the unstable air is coming from the extensive vertical development. So these clouds are saying there is very bad weather around. They're going to create lightning, hail, tornado, gusty winds, wind shear, all that. The worst weather that you could encounter while you're flying a plane. And we'll get more into lightning and hail and tornadoes. They all have their own slides on here, but you just need to know what kind of weather is associated with towering cumulus or cumulonimbus clouds. These clouds have extensive vertical development, so they indicate areas of instability and turbulence. Okay. Good. Okay, here's a picture of different types of clouds. We're gonna get into all of this, and this is mostly what we just talked about. How you have low clouds here, middle clouds here, up here cirrus clouds, the wispy ones over 20,000 feet. Some of these we don't even get into on these slides. We don't have to be meteorologists. We're not going to weather school for all this. We need to know up to a certain amount, but you don't have to go extensively into all the different types of clouds that could ever be developed. So this is just an interesting picture. We'll talk about, has anyone heard of an anvil top on top of a cloud a little bit or remember it from King School? Anyone remember anything about it that's nodding? We'll get into it later, but this has to be the top of this like vertically developed cloud is basically sheared off by the jet stream. Okay. So we'll talk about this later, but because the cloud has reached so high, now the top of it has been sheared off by the jet stream up very high in the atmosphere. Okay. I think this is just pictures and no words on there. So an example, Cumulus clouds are Windows computer clouds. They look like a Windows background, right? Very fluffy. Look like this. I don't know how else to, these are just pictures to help you identify them. Heaped or piled clouds is what they're talking about, like little, what are those things called? Cotton balls? Okay, stratus clouds are formed in layers, so very thin layers of clouds. They don't have a lot of vertical development. These are indicating stable air, right? There's what stratus clouds looks like. Cirrus clouds, like I talked about, are the really wispy clouds, very high in the sky, high level clouds. Ringlets or fibrous, it looks like if you pulled apart like a, I don't know, like pull a cotton ball or something, it would pull apart in like little fibers like this. And lenticular clouds we haven't talked about. So lenticular clouds form over mountain peaks. You see the mountain right here? These only form over mountain tops in strong winds, and they're called lenticular clouds because they're lens shaped, like this, like an oval shape, and it's formed because the air coming up the side of the mountain and then falling over top, like we talked about mountain wave turbulence that happens, that air is pushing up the cloud and then moving on the other side, so it becomes this like elongated circle on top of the cloud, lens shaped. This also indicates because it's formed in strong winds, this indicates extreme turbulence over top of the mountain. So you would not want to fly into a lenticular cloud. Okay. Nimbus, like we talked about, rain-bearing clouds, water. Nimbus clouds have water, they're rain-bearing clouds. They're thicker, they're gray, they're saturated with water. This is what they look like. I'm sure we've all seen rain-bearing clouds. Like I talked about before a little bit, fractal clouds, ragged or broken. So like this is a cumulus cloud, like those puffy white clouds, but it's been like the fractal part of it is it's been fragmented by like wind shear or strong winds coming in and basically like cutting up the existing cloud. It can also happen with like stratus clouds, but it has like jagged edges because it's been like fractured by the wind, basically. Okay. And cumulonimbus clouds, thunderstorm clouds. So huge vertically developed clouds like this. This would indicate a thunderstorm is happening underneath here. Very high vertically developed clouds. You should be able to see them. I don't think the slide gets into it, but from Kingstool, do we know how far we need to stay away from thunderstorms? Yeah. 20 nautical miles. I would double that, but personal minimums, 20 nautical miles. And they love to get you with a question of if you want to fly through the middle of two thunderstorms, how far do you have to stay away? Then you're doubling it, then it's 40 nautical miles away from if you're trying to fly in between two thunderstorms. But 20 nautical miles is the limit for the minimum you have to stay away from thunderstorms while you're flying. 20 nautical miles. Yeah, question.
40 miles on both sides.
Yes, because what's gonna happen from why are they saying 20? Does anyone from King School, why did they say you're staying 20 nautical miles away?
Is it because of wind shears?
It's partly because of wind shears. There's something else that can be thrown out of a thunderstorm, even if you're flying within on the outside of a thunderstorm. Yeah, I see your hand back there. Yeah.
Hail.
Hail. Hail is the main reason why they have you at such a far distance, because hail can be thrown from a thunderstorm all the way and hit your plane, even with your 10 nautical miles away from an active thunderstorm. So even if you're not flying around it will give you wind shear and turbulence and other things that you don't want to fly through. But one of the main reasons is because hail can be thrown from an active thunderstorm many nautical miles away from the storm and hit you in your plane, yeah.
Is that mainly just because of crazy wind speeds?
I would assume so. I don't know the actual,
Because thunderstorms are spinning clockwise?
are they? What's unstable? Which way is unstable air? Like a low pressure system? Which way is a low pressure system moving? Counterclockwise, yes.
Cyclonic, is that why you call it cyclonic?
Yes, exactly. Cyclonic will be low pressure systems, unstable air, moving like a cyclone, because hurricanes move counterclockwise. So that's why they call it cyclonic. And then anticyclonic will be stable air, like a high pressure system that moves clockwise. Okay? Yeah, that went a little bit farther than the slides. I don't know if it comes back to it, but good to know how far you have to say from thunderstorms and why. I think we get into hail a little bit later, but we'll start with air masses. So air masses are classified by the origin in which they originate. So polar region, tropical region, things like that. Large bodies of air that take on the characteristics of the surrounding area or the region, obviously. So, yeah, usually remain stagnant for a period of days or longer. So they categorize air masses over these regions because they remain in this area with these characteristics for a longer amount of time, for periods of days or longer. So during this time of stagnation, when this air mass is over the region, it takes on the temperature and the moisture characteristics of that region. So they have a picture, thank God. So we have Arctic up here. We also have tropical, obviously closer to the equator. And we have Arctic, as well as polar. So continental, it's obviously going to mean land, and maritime means water. Okay. So we have maritime polar, which means polar region over the water. Tropical maritime means tropical over the water. That's why it's characterized as warm and moist air, because it's over the water. Continental tropical is like by the equator. That's going to be hot and dry. It's like desert, barren land, so hot and dry air. Continental Arctic is also going to be very cold and dry land on the Arctic, and then continental polar, cold and dry as well. Okay. You don't have to memorize all these, it's just giving you idea of areas, regions that air masses take on the characteristics of that region before they keep moving. So like you have, we'll talk about fronts, I think today, but you can have the way these air masses move is through fronts like this. So these characteristics of the air masses in that region will take on, if you're over the water in a tropical area, that air mass will be warm and moist, versus an air mass over the continental Arctic will be very cold and dry. Pretty simple, don't overcomplicate it more than it is. So if you have an air mass passing over a warmer surface, then you're warming that air mass from below, which means you're getting convective currents. Remember we talked about convective currents from the ground. The surface is warming faster than the air. You're getting that air rising, warmed from below underneath, causing the air to rise. So this creates, again, unstable air mass, because you're creating warm air that's rising. That rising air is creating instability. Okay? Moist, unstable air creates cumulus clouds. You should know this from before. So unstable air, we talked about the table that you're supposed to write down. So good surface visibility, because that vertical movement is pushing clouds and fog out of the way, so you have good visibility. But you have unstable air means what kind of showers, what kind of precipitation for unstable air. Showery precipitation, thank you. Turbulence, showery precipitation, and cumulus clouds. Okay, that was kind of just a review. Same with this is kind of just a review over stable air. So air passing over a colder surface doesn't form the convective currents from below because it's not being heated from below and rising. So it creates a stable air mass with poor visibility because that if there's any moisture in the air that's creating clouds or fog, that's getting stuck there because it's not moving with stable air. So smoke, dust, and other particles cannot rise out of the area, so you end up with poor visibility. Okay. Okay, now we're on to fronts. You must know this. The other stuff that we just talked about is good to know as backup, but you must know the different types of fronts. You need to identify one, what they look like on a prognostic chart. So we have the different ways that they look on the prognostic chart, and we need to know how they move across the US specifically. So we have warm and cold fronts, stationary fronts, and what's called an occluded front. So there's a slide for each of these, so we'll get into each of these specifically, but no, there's 4 of them that you need to know. These fronts are the boundary layer between 2 types of air masses, okay? Let's start, okay. Do we have a picture? Okay. I guess I'll draw it. Do some drawings. Okay, warm front looks like this. But filled in. Pretty sure it's yeah, filled in. So the red little bubbles are filled in. This is a warm front. So what you need to remember about a warm front and how it moves is you need to think about a blanket. A warm front moves like a blanket. So it moves slowly. It moves slowly and typically, here we go, slowly, 10 to 25 miles per hour is considered slow. So a warm air mass advances over a body of colder air slowly, like a blanket covering the cold air. A warm front comes in and covers on top of cold air. That's how a warm front moves, okay? What else? Yeah. Slides over top of the cooler air and pushes it out of the area. So a blanket that moves slowly over cold air and pushes it out of the area. Often has very high humidity. That was the help. And as warm air, as we know, as warm air is lifted, the temperature drops and condensation occurs. So generally, prior to a warm front, you could have cirriform or stratiform clouds along with fog. And in the summer months, you could have cumulonimbus, thunderstorm clouds are likely to develop because these warm fronts contain warm air that has very high humidity. So it's got that moisture to create clouds and fog. Okay? We need to remember it moves slowly, comes on top of colder air, pushes, gradually pushes that out of the area. It looks like the red line with red dots on one side, and you can think of it like a blanket that moves over top of colder air. Okay. Okay, warm air here is moving on top of the colder air underneath. And that warm air can create, that warm air is moist warm air, so it can create clouds ahead of the front. Cold fronts, to think about, you can think about a snowplow, how they move. And it looks like this with little triangles on the front, and it's blue, and the triangles are filled in. Okay, so when we're talking about a snowplow, how it moves, it's going to be cold, dense air that advances and replaces a warmer body of air. But it moves like a snowplow because it comes in from the bottom and pushes that warm air up, like a snowplow, moving it upward. So it comes in fast. Cold fronts move faster than warm fronts. It moves in fast, and it's a cold, dense body of air that comes in and pushes up a warm mass of air. And obviously, every time we talk about warm air being pushed up, creating vertical development, this is going to create instability in the atmosphere. So move rapidly, 25 to 30 miles per hour. It's cold, dense air that advances and replaces a body of warmer air. So they actually have been recorded to be moving up to 60 miles per hour, which is very fast, but it's opposite of that which we talked about a warm front. So it's so dense, it stays close to the ground. And like I said, snow plow sliding under the warmer air and moving it up, forcing the less dense air up. So rapidly ascending air, like we've talked about, causes the temperature to suddenly decrease and forcing the creation of clouds. So as a cold front passes, you get towering cumulus or cumulonimbus clouds because you're creating that vertical development, right? You're snow plowing that warm air up, the temperature decreases and it creates clouds. So that vertical development from the clouds is created from the cold front pushing that warm air up. Make sense? Everyone following? Cold front, snow plow. Okay. Oh. Okay, here it is. See how it's coming here? It's very dense. It starts at the bottom. That cold, dense air is coming in. It's going to push all of this warm air up, creating towering cumulus clouds and cumulonimbus clouds with lots of vertical development because this cold air is moving all this warm air up. Okay? Stationary fronts, it already has it on here, so I don't have to draw it. It's going to be a mix of what I just drew. So the red bubbles and the blue triangles, it's just going to go back and forth like this, blue triangle, red bubble, blue triangle, red bubble. Stationary fronts is when the two air masses have like a standoff with each other. So a cold air mass is meeting a warm air mass, and once they meet, they're having like a standoff, and neither one of them moves the other one out of the way. So it ends up being influences the local weather for days. It ends up remains stationary. So it's in the name, stationary front. It works like a standoff where they're kind of both pushing against each other. They're relatively equal, and thus it remains in that area. Whatever weather remains in the area for days because neither one of them is moving the other out of the way. Okay. Oh yeah, I see your hand.
Would that be the neutral air, or would that be considered stable?
It depends on the mixture of the air, but I don't know exactly. I think
In
it
other words, how
depends.
would we know if it's neutral. I get the stable and unstable.
Yeah.
But for it to be neutral, they have to be equal, right?
Yeah,
So,
I think it's going to depend every time on what weather is produced based on, because it's rarely ever going to be completely equal. So it's going to be based on whatever weather it creates, based on the cold air mass and the warm air mass. If that comes together in an unstable way and you have vertical
yeah,
development and turbulence, that means that because of the warm mass staying there, it will stay in that area for a longer period of
so
time.
it's still
That's just-
unstable.
It's still unstable if that's what it creates at the time. But then because they're both working against each other, it's going to be unstable for days
Okay.
instead of, most of these are moving out of the way pretty fast.
Pretty hard to have like a,
I think, yeah,
okay.
I've never heard of a fully neutral stability on that. Okay, last one, occluded fronts. Is purple. Purple little bubbles. And an occluded front is when a fast, because we know the cold fronts move fast, a fast moving cold front catches up with a slow moving warm front and basically pushes that warm front up into more cold air. So it's kind of like a sandwich of cold air in between a warm front. So as the occluded front approaches, warm front weather prevails, but is immediately followed by cold front weather. So it's like a back-to-back hit of warm front weather and then immediately cold front weather, which usually results in very bad weather. Occluded fronts are known, are known to be indicators of extremely bad weather, thunderstorms, unstable air, things like that. You see cold air on this side is coming in really fast, pushes up warm air. It's got more cold air on the other side. So it's two cold air masses sandwiching a warm air mass upwards. And it's got two. They don't back here. This is the purple line for an occluded front. Cold front overtakes a warm front. And I'll actually, maybe by the end of class, but to find a prognostic chart or a prog chart, we can go to aviation weather, products, prog chart. And this is where we find all of the symbols that we just looked at. If it will load. Hello? Okay. This is disappointing. What happened to the Wi-Fi? Okay, there it is. Okay, you see this purple line right here? It actually has alternating circles and triangles. But this is an occluded front. What's this one? This blue. Cold front. What's up here? What's this one? Stationary front, because it goes back and forth from red and blue. Means the cold front is at a standoff with a warm front. And down here is also a stationary front. And there's just a tiny little, which one's this on the end? Tiny little warm front down there. So mostly stationary cold fronts along, and then we have one occluded front over here, over the top of California. Yeah.
It's a warm.
We'll get into it, but this is called a trough. It's an area of elongated low pressure. So you'll always see it coming off the L's for low pressure. So it's a elongated line or area of low pressure. It's called a trough. 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 Okay. There's also something called a dry line that I don't see on here. That's usually over Texas. It's like a yellow, orangish line with circles on one side and then the straight line on the other. And the circles on one side indicate where the moist air is on one side and the dry air is on the other. It's called a dry line. I don't think it's in the slides today for some reason, but yeah. This orange line is a trough, and you can see it's literally connecting all these low pressure areas because it's in an elongated area of low pressure, following all here. While we're here reviewing, how does a low pressure system move? Which way is it moving? Counterclockwise, this way, right? And high pressure down here, which way is it moving? Clockwise this way. So we'll get into, can I actually draw this? Oh yeah. Yes. So we'll get into here, but since I'm already drawing it, if you wanted to fly between if you wanted to fly here between, where would you fly? Was the best? Let's keep going. If you wanted to fly between here, would you fly under the high pressure system or on top of the high pressure system? If you're going east to west. Top. You want to follow the flow of air. You fly on top of it. Same with low pressure system. If you know the low pressure system is moving counterclockwise, then you can decide to fly above or below the low pressure system. Low pressure system below, moving east to west, will push you along, give you like a better tailwind underneath than.
Wait, that's backwards.
Which
That-
one?
Because if we're.
Oh, the way I drew it?
No, we're moving. So, yeah. You're thinking west to east.
Oh, okay, sorry. West east. Okay. There's gotta be a slide on it, but we'll go back. Okay.
So if you were going east to west, you would have gone. You're trying to go.
You wanna follow the flow of that it's turning. Does that make sense? You wanna follow the arrows. So if it's turning clockwise, you would go on top to follow the flow of the arrows instead of underneath. That makes sense, right? You have to go all in. If it's moving clockwise like this and we fly on top of it, we're following the arrows moving clockwise, right? This way
And then the other arrows then are going the other direction. So,
for low,
right,
this way.
you'd said.
We fly, yeah. I was thinking if we're flying east, following the arrows, if you're flying east to west, underneath, you would follow the arrows, but it was backwards. If we're flying on top of it, we want to fly west to east. Same thing. Follow the arrows is what we're talking about. Okay. Okay, convective activity we already talked about, right? Convection is when the warm air rises. So that's the development of convective clouds from the rising of warm air. Radiation they have on here as heating the ground, and conduction happens when the ground heats the air. So manifestations of convective activity is what poses the greatest threat to aircraft because it's creating that upward motion is creating showers, thunderstorms, hail, tornadoes. Squalls means squall line thunderstorms. Squall line thunderstorms are basically a line of thunderstorms that move together. If you've seen it on radar before, on like the Weather Channel, it will be a line of thunderstorms that all moves together. Those are squall line thunderstorms instead of one area, single thunderstorms. So obviously very dangerous. It might get into it here. So a thunderstorm obviously has thunder associated with it. You can't have a thunderstorm without thunder and lightning. Thunder comes from lightning, so you're gonna have lightning. All thunderstorms have lightning and thunder. So it's classified as severe when it contains one or more of the following. So we talked about hail is created in thunderstorms, and also turbulent wind in an excess of 50 knots or greater, or in the most extreme case, or tornado can be formed from a thunderstorm. Yeah. Spring and summer months, here we go. At least 20 nautical miles away from a thunderstorm. Okay. What are you doing in here?
Right.
Okay, embedded thunderstorms. So, inside a thunderstorm, there can also be smaller areas of thunderstorms that are embedded inside, that are not visible inside the clouds, hidden inside a thick line of clouds. Here. Hidden inside a thick line of clouds. So, obviously, this is the most dangerous threat to us in the air because we are not able to spot it visually. Like usually with a thunderstorm, you're able to spot from a distance that vertical motion, and you can see kind of like a tower of clouds being created for a thunderstorm. These embedded thunderstorms are hidden inside other clouds, so they're posing obviously a threat to anyone within, again, 20 nautical miles of these storms. Let's keep going. Okay, back to squall lines that I mentioned before. A system, here's what it looks like on the radar. I'm sure you've seen this on the Weather Channel radar before. It's a system of thunderstorms that has formed into a line. And what we want to know is it usually occurs ahead of a cold front. And where wind shear combined with like widespread lifting action causes convection to become arranged in like a band of thunderstorms is what's created. So it's occurring ahead, usually occurring ahead of a cold front, and wind shear combined with like a long line of lifting action creates like a long band of thunderstorms. This is squall line thunderstorms. Okay, write this down. Requirements for a thunderstorm. Very important. Unstable atmosphere, lifting mechanism, and sufficient moisture. You will be asked this on phase checks and a check ride. You will ask what's the requirements for a thunderstorm, and you have to list each one of these. You need an unstable atmosphere, a lifting mechanism, and sufficient moisture. So if we were to talk about what each one of these, where it comes from, so how can we tell if the atmosphere is unstable for a thunderstorm? Just by looking, or if we find information from like a METAR or something. Yes.
So there's a certain type of cloud that start of the sea,
Yeah, cumulus.
clouds that are extending upward, right?
Yes, cumulus clouds with vertical development. Very good. That can be an unstable atmosphere. What's a number that we can look at for unstable atmosphere as well? You said ooh.
I wanna say it's the one that starts with the I that they're talking about yesterday.
An I?
Or sorry, an M. Like they're called really at the chart.
Does anyone know? Sorry.
No, this is not the pressure number that was on the front chart.
It's not the pressure number. It has to do, not the METAR, it has to do with the rate.
Lots.
The lapse rate. So we have a standard lapse rate, right? 2 degrees Celsius per 1,000 feet. Anything outside of 2 degrees is non-standard. That can be an indicator of an unstable atmosphere. Okay, so a lapse rate can tell us if we have an unstable atmosphere. The clouds outside can tell us about an unstable atmosphere. What about a lifting mechanism? What's an example of where we can get a lifting mechanism from? A front, good. Which kind of front is the most lifting? Cold front, good. Cold front is a lifting mechanism. Also, we'll just start with cold front on this. So we have an unstable lapse rate, or we have cumulus clouds telling us we have an unstable atmosphere. We have a cold front that's creating our lifting mechanism. And then how can we tell if there's sufficient moisture in the atmosphere? Dew point. The dew point, the temperature and dew point spread. The closer those numbers are, like we talked about, the more moisture there is in the air, especially if those numbers are the same. That means that the dew point has reached the temperature. The atmosphere is saturated with moisture, so you have sufficient moisture for the formation of clouds, which is a requirement for a thunderstorm. So this is where we find examples of all this, how we figure out, do we have these 3 ingredients? But you need to have these memorized: unstable atmosphere, lifting mechanism, sufficient moisture. So also lifting mechanism, it gives you an example here. The sun is heating the surface of the earth, which warms the air right above the surface. And that warm air is forced to rise around a hill or a mountain. Then that area can be moved into wet air, which causes a rising motion. So it will continue to rise as long as it weighs less than the warm air around it. So this is what they're talking about. If warm air is forced to rise up the side of a hill or a mountain, then that rising motion will continue as long as it weighs less than and stays warmer than the air around it. Because water vapor, water molecules are heavier than air molecules, right? So if you get too much moisture in the air, it will weigh more than the air around it. Also, example gives you, as air rises, it transfers heat from the surface of the earth to upper. Okay, so convection, like we just talked about, that's rising warm air, water vapor begins to cool, releases the heat, and condenses and forms a cloud. We already talked about this. So convection can create, with water vapor, can create the lifting mechanism and sufficient moisture in the air, forming a cloud. And as the cloud continues that vertical motion, grows upwards into areas where the temperature is below freezing. Okay. Here's the 3. Okay, then outside of the 3 ingredients of a thunderstorm, we need to know the stages of a thunderstorm. So the first is called cumulus, or the developing stage. Then you have the mature stage and the dissipating stage. Okay, this is what it looks like here. We'll get into each of them individually. Okay, first stage of a thunderstorm is called the cumulus, or the developing stage. This stage is categorized by updrafts. Updrafts. So little to no rain during this stage. You could have lightning, but we need to remember the first stage of a thunderstorm, the developing stage, is categorized by updrafts, rising columns of air. Okay. Cumulus cloud continues to rise. Soon it looks like a tower. We've created a towering cumulus cloud as updrafts continue to develop. So, developing stage, cumulus stage is the stage characterized by updrafts. Mature stage of a thunderstorm is characterized by rain. So precipitation begins to fall out of the storm. Post here. So the mature stage is categorized by precipitation. This is when rain is seen during the mature stage of a thunderstorm. So as precipitation begins to fall, it's beginning to create downdrafts. But the main part of the mature stage is the rain is falling. Precipitation is falling. Downdrafts and rain-cooled air spreads out along the ground. It can also form like lines of gusty wind. Most likely time for hail, heavy rain, frequent lightning, strong winds, and tornadoes if you have an extremely severe thunderstorm, but mostly mature stage, you're going to see rain, okay? Last stage is the dissipating stage of a thunderstorm. This is categorized by downdrafts. So really simple to remember this. The first stage, the cumulus or developing stage, is categorized by updrafts, creating that vertical development, the towering cumulus cloud. The mature stage is when it rains, so it's letting go of all that moisture it was holding, and the dissipating stage is characterized by downdrafts. So we just talked about rainfall decreases in intensity, lightning still a danger in the stage, but then you're getting back to at the ground, you can get what's called a gust front that moves out along a distance from the storm, cuts off the warm, moist air that was feeding the thunderstorm underneath. But downdrafts are is what characterizes a dissipating stage. Yeah, the updraft is overcome by the downdrafts that start at the dissipating, okay? Updraft, precipitation, downdraft for all of these. Lightning. Yeah, lightning's not great for an aircraft. Obviously, we have a lot of navigational equipment. We run a basically fully electric system in the sling. Lightning can blind you from a distance if you look directly at it. We don't have a magnetic compass, but if you were flying an older plane that had a magnetic compass, you'd be worried about nearby lightning and produce errors in the magnetic compass. I think we'll get to compass errors way later on when we talk about cross-country flight planning, and can disrupt radio communication on low frequencies. This is all just good to know. You don't have to memorize this. Does anyone know how lightning is formed? I learned this recently. Do what? Someone say friction? Friction of what? Friction of clouds? It's not the clouds, it's friction of the molecules, right? So we talked about, yeah, exchange of electrons to the molecules. So they're moving so fast, they're creating static electricity that creates we talked about the molecules moving really fast when they're heated up and they expand. And then as they're bouncing against each other, they're creating static electricity. The electrons are creating a charge, and that creates the electricity from the lightning. It's kind of interesting. You don't have to know that. I just learned that recently. Tornadoes. Okay, tornadoes can occur with both isolated and squall line thunderstorms. So we talked about squall line is like a band of thunderstorms and a line. Isolated is obviously isolated thunderstorms. Reports for forecasts of tornadoes indicate that the atmospheric conditions are favorable for violent turbulence. I think we know that. So we shouldn't ever be in the air when there's a tornado warning. They're pretty good about predicting tornadoes through like convective activity in the area. But what's important to know from this slide is if for some reason you were in the air, you cannot fly over top of a thunderstorm. It looks like a thunderstorm or tornado. A tornado looks like it's like one vortex that has like a top to it, but the vortex extends well into the clouds above it. So even if you, for some insane reason, were thinking about flying on top of a tornado, it extends further than you're able to see. It extends all the way up into the cloud bases, not just on top of the ground where the vortex is. So flying above it, you're probably caught in a severe thunderstorm. You would encounter a hidden vortex up there. I think that's the only thing they're trying to tell you here. We're not really worried about tornadoes out in California. Turbulence, we've talked about a bunch of different ways, but turbulence is present, hazardous turbulence is present in all thunderstorms. So severe thunderstorms can destroy an aircraft with turbulence. The wind shear between updrafts and downdrafts is particularly dangerous. Yeah. Turbulence has been counted several thousand feet away and 20 miles laterally from a severe storm. Again, this is why we're talking about staying 20 nautical miles away from a thunderstorm for turbulence and for hail. Okay? A roll cloud can be on the leading edge of a storm and marks the top of the eddies in the shear. I'm not even sure what an eddy is. Does anyone know what an eddy is? Eddy. Nobody? Eddies. Eddies are swirling patterns in fluids, like water or air, caused by obstacles or changing currents. Okay. Eddies are swirling patterns of air caused by changes in currents. Interesting. Okay. Levels of turbulence are pretty important because when turbulence is reported to us by, especially by other aircraft and like pilot reported like PIREPs, the level of turbulence can change based off of the different types of aircraft, right? So the way a sling flies in light turbulence is different than the way a sling flies in severe turbulence. Like a jet compared to us for light turbulence is a huge difference. So they have definitions on here for light is small erratic changes in altitude or attitude. Moderate turbulence is a change in altitude, but the aircraft remains in positive control. And then severe is abrupt changes where you may be momentarily out of control. Extreme, you're violently tossed around, may cause structural damage. So extreme turbulence in the sling might be reported as moderate turbulence for a jet, right? So it's just increasing severity of turbulence. Mainly the difference between small changes in altitude, but the aircraft remains in positive control versus the aircraft is uncontrollable for either moments of time or for the entire flight. Okay. Oh, 30 minutes, okay, I think this is some of the last slides. For icing, we talked about super cooled water droplets and how, because they're still water droplets, the fact that they're super cooled means they freeze on impact when they fall on top of the surface of an aircraft. So we have, do they have a slide about this? Okay, they have types of icing, but there's clear and rime icing that we're gonna talk about. The differences in those. Let me see if there's something. Okay, I think actually first we're gonna start on here. So types of icing, we have clear ice and rime ice, and then you can have a mix of clear and rime ice. So write these down. Clear ice, obviously they're talking about clear in color. It mostly develops from super cooled large droplets of water. They don't have super cooled in the slide on here, but that's important to know is clear ice is super cooled large droplets of water. And they freeze like an icicle because they run back along the wing. So clear ice is the most dangerous type of icing for the aircraft because these are large droplets of water that are super cooled. So they hit the wing, let's say on the leading edge of the wing, and they roll back towards the trailing edge of the wing. And as they roll back from the leading edge, because they're still in water form, right? They haven't frozen yet. As they hit the leading edge, they roll back to the trailing edge and they freeze along their trail back. So they create like a sheet of ice on top of the wing because it freezes as it's rolling back across the surface of the wing. Why do we think this is the most dangerous type of icing? Any ideas? One, we can't see it. Yeah, it's clear ice, so it's hard to see. Two, what did I just talk about? It's freezing in like a layer over top of the wing, right? It's not freezing on impact. It's a large droplet of water, so as it hits the front leading edge, it's able to run back and freeze in like a sheet. Yeah. Yeah, disrupts airflow over the wing, and then another really important reason, it's creating a sheet of ice. Oh, hold up. Hello?
Yeah, I
Hello?
was on this for a while.
Okay.
But yeah, like, he's up to that controls.
Yeah, running back, what's in the back of the trailing edge? Our control surfaces, right? Our ailerons and our flaps. So that freezing water is coming back onto our control surfaces and freezing. And then I guess an even more reason on top of that, creating a sheet of ice on top is disrupting airflow, but it's adding weight, right? We're adding weight that we're not accounting for on the top of the wing. Okay, all those reasons. It's clear, so it's hard to see until it's already formed on top of the wing. It's creating a sheet of ice over the top of the wing because it's hitting the leading edge of the wing, rolling back towards the trailing edge and freezing as it rolls back. That's creating a sheet of ice which is added weight. It's changing the airflow over the wing, over the surface of the wing, and it's also able to freeze our control surfaces because that water is able to move further back towards our ailerons and our flaps before it freezes. Okay? Rime ice, on the other hand, is milky in color, so you're able to see it better. And it's mostly smaller water droplets that freeze on impact when they hit the aircraft. So rime ice is going to build up on the leading edge of the wing. So it's not going to roll back towards our control surfaces, but it will disrupt airflow because it's creating like hard ice that impacts on the leading edge. It's going to create like a hard surface on the leading edge of the wing, which is going to disrupt airflow, disrupting lift, because that airflow has to flow over the leading edge to get those wingtip vortices. It's always circulating around the wing. So if we have disrupted airflow on the leading edge, that's also going to impact lift being created, it impacts airflow. So rime versus clear ice, and then there's just mixed where it's just a mix of both. You're getting both developments of sheets of longer clear ice and rime ice that develops freezing on impact. Okay? Does this make sense for clear and rime? Why clear is the most dangerous? Good. What else do they want to say? Okay, you should be alert for icing anytime the temperature approaches 0 degrees Celsius and visible moisture is present, right? Icing is freezing temperatures plus visible moisture, right? Clear icing can occur at any altitude above the freezing level, but at high levels, icing from smaller droplets may be rime or mixed. Because the higher we go, the colder it gets, you might have more rime ice that freezes on impact. Because like we talked about, clear icing is those large, super cooled water droplets. So the higher you go in altitude, it's going to become just a frozen water droplet instead of an actual source of water. It's going to become just freezing on impact ice. Okay, back to this. Did everyone get this? Some people are still writing. Okay, back to hail for a minute. Hail, like we talked about, is why we're concerned about staying so far from a thunderstorm. Hail can be encountered several miles away from thunderstorm clouds. So, yeah, as hail falls into warmer air, it can melt and become rain. Hailstorms, obviously, if they're above freezing temperatures, they begin to fall into warmer air. They can reach the ground as precipitation, as just rain. So rain at the surface of the ground does not mean that there's not hail up higher, right? Because it's just liquefying to a water as it gets closer to the ground because it's heating up, but that means higher up there can still be frozen hailstorms in a thunderstorm. Okay. Yeah, you should anticipate hail with any thunderstorms, but especially beneath the anvil of a large cumulonimbus. Do we remember the anvil that I talked about? That anvil top is where the jet stream kind of cuts off the top of the cumulonimbus, like a towering cumulonimbus cloud. So it looks like this, there's the cloud, and then it has like a weird top, like this, where the jet stream is flowing. This way it basically shears off the top of a towering cloud. So you should especially be anticipating hail if you see an anvil top on top of a large cumulonimbus cloud. And that just gives you an idea of how large hailstones, larger than even 1/2 inch in diameter, can obviously damage the aircraft a lot. Okay, feel good about hail? We'll get back. Okay, we're done. Do we have any questions? That was a lot of slides. I think tomorrow is just going over most of it, but we started with fog. Do we understand fog? What's the most common type of fog we're gonna see here at Torrance? Advection fog.
Could you describe that as the labeling?
Yeah, the marine layer coming in is advection fog. Let's get back to what. Does someone remember how steam fog works? Steam fog over the water. It's like the opposite of advection fog.
The water's warm
Mhm.
and there's cold air blowing over it, pushing those warm air lines.
Yes. Cold, dry air from the land is pushing over warm, moist air. I'll go back to here. So then as the water evaporates, it rises and resembles smoke on top of the water. Okay. Let's- Where can we find lenticular clouds? Say again? Mountaintops. Good. Okay, warm fronts. How does a warm front move? Slowly, good. What else?
A blanket.
Like a blanket, good. So it moves slowly over top of cold air. Okay. What about a cold front? How does it move? Fast and like a snow cloud. Good. So it moves fast. It's cold, dense air that moves fast along the ground and pushes up warmer air, creating that vertical development. So you're gonna have bad weather from that vertical development. What are the 3 ingredients to a thunderstorm? Everyone's feeling shy. Someone raise their hand. Front rows already answered. Someone in the back row answered. Omar, go. Unstable. Uh-huh. Yes. Unstable atmosphere, technically more than just air. Unstable atmosphere, a lifting mechanism, and visible moisture is technically what we're talking about. Visible moisture is gonna be from either clouds or that dew point and temperature meeting. What else? I'm technically not supposed to let you all go before 15 minutes left of class, so we have 5 more minutes left of asking questions. Okay, what is the first stage of a thunderstorm? Cumulus. What is the what characterizes the cumulus stage of a thunderstorm? Yeah, Alex. Updrafts, good, easy. Updrafts for the cumulus beginning stage of a thunderstorm. What's the second stage of a thunderstorm? Yeah, Jake. Mature stage. What is categorized by the mature stage? By rain. Good. Last stage is what? Go ahead, Jason. Dissipating stage characterized by downdrafts. Good. Updrafts, rainfall, downdrafts is the 3 stages of a thunderstorm. Okay. There they are. What else can I ask? What do we remember about radiation fog? Anyone? First thing we talked about. Radiation fog.
The heat from the
Uh-huh. That's all I got? Okay. Something. Okay. So, who's talking? Okay, go ahead. It's actually that's gonna be steam fog. The ground is actually heated from, like, during the day. The ground's heated by the sun, and then the ground's gonna radiate heat off of the ground. And then as it rises off the ground, it's gonna cool to its dew point, and that creates fog right over the ground. So it's warm air from the heated ground is rising, reaching its dew point and condensing into clouds right on top of the ground. Okay. And do we have wind with radiation fog? No, no wind. So it would just push the radiation fog away. So no wind. It's also on clear nights. So think calm, clear nights, meaning calm meaning no wind, calm, clear nights, the warm ground that's heated from the sun during the day, now it's at night, and now the ground is warmer than the surrounding air, so that air rises off the ground. As it's rising, it's cooling, and it cools down to its dew point. It condenses into a cloud, and that cloud is fog right over the ground. Okay? No wind, clear nights. Meaning if there were other clouds in the sky, the clouds, when that air reaches the clouds, it would just bounce back that heat and it wouldn't be able to cool to its dew point, right? So clear nights, meaning no other clouds in the sky, that air is being heated from the ground. The radiation from the ground is heating the air, but as it rises, it cools to its dew point, creates a cloud. I think that's mainly it. What are the different, okay, what are types of low clouds? It's an example of a low cloud. Alto is middle, so not middle. What about low? Stratus. Stratus, stratocumulus, or nimbostratus. It all has stratus or strato in it. Stratus clouds, stratocumulus, nimbostratus. Middle clouds, who said alto last time? Good. Middle clouds are the altostratus and the altocumulus. Alto meaning the middle, same type of clouds, but they're just middle level. It's going to be from 6,500 to 20,000 feet. And then examples of high clouds. Cirrus clouds, good. Cirrus clouds, cirrostratus, and cirrocumulus. Okay. I've got 1 more minute. Somebody ask me a question. Okay. Occluded fronts. How do occluded fronts work? How do they move? Anyone? Cold air moves into warm air and it pushes it up, right? It's pushing it up. Yes. So where's the occluded front? That cold air that's moving fast catches up to a slow moving warm front and pushes that warm front up, creating vertical development, but it also has cold air on the other side. So it's kind of sandwiching cold air between warm air. This creates a lot of bad weather because of the vertical development and the fast moving. It also creates warm front conditions followed very quickly by cold front conditions back to back. So you get hit with multiple weather occurrences back to back, which is why it usually is indicating bad weather on a prog chart. Okay, lastly, what about stationary front? And then we can go. Stationary front. Someone else that hasn't spoken today. Yeah, go ahead. Yeah, they're in a standoff, right? So it's gonna be a warm front and a cold front, not just cold and warm air. A warm front and a cold front move together, they're at a standoff. Neither one of them is strong enough to overtake the other. They're not always going to be perfectly equal, but they're equal enough that they're not able to move the other one. So they have a standoff, creating some type of weather, and that weather is going to be stationary over that area for multiple days. Okay? All right, good job, everyone. See you tomorrow.